Hello, everyone. We are very happy to have you all here. And to begin today's seminar, I would like to introduce you to the Director of UCAR Community Programs, Scientific Programs and Services Center, and the Director of CPAESS, Hannah Moriello.
Thanks for the introduction, Dawn. Welcome, everyone. We are delighted to have you attend the CPAESS Discovery Seminar Series. Before we begin, I would like to briefly welcome Dr. Cindy Bruyere, our new CPAESS Deputy Director.
Thank you very much, Hannah. It's a pleasure to be here, and I'm looking forward to the talk today.
Thank you, Cindy. So this series began to share the impressive breadth and depth of the research from CPAESS scientists who study the entirety of Earth system science. We have scientists who do everything from explore our ocean depths, to fly into hurricanes, to take critical measurements, to heliophysicists modeling coronal mass ejections, to those who unravel the mysteries of the Arctic. And we want to share this with the public, the NCAR community, and our many colleagues at universities across the globe. Just to orient you all, we are using Slido, so you can post questions for our speaker, which you can type in at any time during the seminar. The Slido window is located below this presentation screen. And do not panic if you do not see your question pop up, as we are holding questions until our speaker completes their presentation. Questions will be revealed later during the Q&A portion of the seminar. So it is my sincere pleasure to introduce to you today's speaker, Jan-Huey Chen. Dr. Jan-Huey Chen is a UCAR-CPAESS project scientist working at GFDL in Princeton, New Jersey. Much of her research focuses on tropical cyclone prediction on weather to seasonal timescales. Her most recent publications have discussed the improvements on tropical cyclone forecast skill in the United States' next generation global prediction system. Her results demonstrated that the quality of initial condition is the key element of the ECMWF to achieve the best hurricane track forecast in the world. She's one of the key members of the GFDL FV3 development team, who has been involved in the development of several models, including HIRAM, HIFLOR, AM4, SHIELD, and SPEAR. Her current research uses different SHIELD configurations ranging from kilometer scale, telescoping, NEST SHIELD to global 25-kilometer S SHIELD for tropical cyclones, severe weather, and prediction in weather to subseasonal and seasonal predictions. Dr. Chen received her PhD from the Department of Atmospheric Sciences, National Taiwan University in 2009. She has been with DFDL since 2010. Today, Dr. Chen is speaking on tropical cyclones in the DIMOSIC project, and please join me in welcoming Jan-Huey.
Hi, everyone. Could you hear me well? Okay, thanks a lot for Hannah's introduction. I try to move the slides forward. I'm sorry, I couldn't do it. Oh, okay, good, great. Okay, sorry about that. I'm very happy to have this opportunity to share our tropical cyclone results in the DIMOSIC project to the entire UCAR community. And before I start, I would like to give my special thanks to my GFDL colleague, Lin Zhongzhou, and the ECMWF scientist, Lennox Magnuson, and the entire GFDL FV3 dynamical core team for their kind support. And I first would like to give you some background about the DIMOSIC project. And actually the story could be traced back to 2017. Professor Fuqin Zhang, who in Penn State University at that time, who unfortunately passed away 3 years ago. I know many people in Boulder also know him a lot and cooperated with him a lot. And he came out with an idea, and he would like to use our GFDL shield to investigate the impact of using different initial conditions on model predictability. And you might often heard people do similar tests using different initial conditions to test. Usually they do in the regional models, especially in the research type regional models. But keep in mind that it is not an easy task for a global general circulation model. For them to correctly ingest the initial condition created by another GCM is tricky. Therefore, during the collaboration with Fuqing Zhang, we carefully implement the function in our shield model to be able to use both NCEP GFS and the ECNWF IFS model as the initial conditions. And in 2018, the next visitors, we come out with some research topics. In the next year, we published 2 papers in Chen and O 2019 in GRL. We talk about the tropical cyclone forecast. And the other one was the Magnuson and O 2019, and he talked about the large scale predictability in weather timescales. So from these 2 studies, another question can be raised is if we can do the things the other way around, using different models, but same initial condition, then we might be able to answer the question is, where and when does those model differences play the largest role on model's predictability? Therefore, in 2019, since 2019 summer, the DIMOSIC project was initiated and has been led by Lennox at ECNWF. That's called different models, but same initial conditions. All the participating models use the same initial condition provided by the ECNWF to initialize their model. And we would like to focus on the 1-year period from 2018 June to 2019 June. All the models will run their 10-day forecast every 3 days at 00Z and initialize the using the ECNWF IFS initial conditions. In our recent paper, Magnuson et al. 2022 is almost accepted. We just got a news this week. We listed 2 questions that this project would like to answer. First, how much differences does the choice of model formulation make for the forecast quality? And can one identify models that are more similar than others? So in this study, I would like to assess this setup scientific goal by taking a look at the tropical cyclone forecast. There are 7 institutes and models participating in this project. 2 configurations from ECNWF IFS model. 46R1 is the configuration, operational configuration back in 2018 to 2019, the DIMOSIC project period. And the 47R3 is their current operational configuration. We use the same configuration to rerun the whole period. And we have DWD's ICON model from Germany. We have our project from France, and we have United model from British, and back to the US. And we have our GFDL shield model. And in Canada, they provide CMC operational runs. And JMA's GSM model is from Japan. And for the tropical cyclone forecast comparison, all the model outputs are interpolated into half degree for easier comparison. And we run the GFDL simple tracker with the Wonko criteria to try to find the tropical cyclones in all the model forecast. Before I show you the tropical cyclone forecast result, I would like to jump to give you a brief introduction about our GFDL shield model. And it is a system for high resolution prediction on Earth to local domains. We focus on weather to seasonal forecast applications. This global uniform 13 kilometer resolution configuration is the one we're using for the DIMOSIC project. And it is also our mothership configuration. Based on this configuration, we have been created 6 different configuration and breeds for different for different research purpose. From a 25-kilometer resolution for subseasonal to seasonal prediction to 3 kilometer globally for global cloud resolving simulation. And we recently just created this Taylor shield configuration, use the telescoping grid nesting function, and to create 1.3 kilometer resolution around the Taiwan area to support the Precipitation 22 field campaign led by Michael Bell in CSU. And you can check our 4 times daily forecast for 5 to 10 days for different configuration and on different target area on our near real-time website, shield.gfdl.noaa.gov. Okay, so about the tropical cyclones in a DIMOSIC project. This figure shows all the best track on the map during the entire DIMOSIC period. We have 16 tropical cyclones in the North Atlantic, 24 in the East Pacific, 35 in the Western Pacific, and 27 in the Southern Hemisphere. So later I'm going to show you the result, mostly just based on these 4 major basins. And I'll show you the forecast of tropical cyclone on their track arrow, related precipitation, intensity, and the genesis scale in all the DIMOSIC models. First is about the tropical cyclone track forecast. Here is the global average track arrow along with the lead time. It is a homogeneous comparison. So the case number are listed below at the bottom for every lead time. That's the number of comparison case numbers. We can see that the differences between the models are very small before day 3, the 72-hour lead time. Only the CMC has a slightly larger error during this period. After day 3, the models start to show some diverge. The IFS, SHIELD, ICON, and our project show lower, smaller errors than the CMC, and JMA models from day 3 to day 5. After day 5, the model diverge more, but the two configuration of IFS are still consistently showing lower errors than other models. So to better show the differences between these leading performance models, here I plot the track arrow differences to the IFS 46R1 configuration, that's the black line here. From this plot, we can see the new IFS configuration, the red line, steadily showing a equivalent or even better performance than the IFS 46R1 configuration. The German ICON model, SHIELD model, and our project also did very good job. SHIELD showed the lowest error between the day 2 to day 3, and the ICON did very well until day 5. Okay, let me go back here. So why I list the UN model here, because this model shows some pretty interesting results, and we can see that from this track arrow average plot during the first 5 days. For global average, we can see the performance rank is just like what I just shown, but in the North Atlantic basin, we see the model shows the lowest error is not the IFS model, but the UN model. However, the UM shows a much higher track error in the East Pacific. On the other hand, in the East Pacific, SHIELD did a very good job, but we also see the SHIELD model doesn't do that well in the Atlantic basin. And I have did some investigation about this issue, and I will show you later, just in the next 2 slides. But in general, the models from CMC and the JMA, unfortunately, they didn't do well. They didn't well capture the tropical cyclone movement in this 2018 to 2019 season. Okay, so what happened on shield in this 2018 North Atlantic hurricane season? So this is the track error along with the lead time for only the Atlantic basin. We can see shield show, if this one is comparing to the IFS model, we can see shield show a relative high track errors from 84 hours to 133 hours. And we find the reason is, although there are 16 tropical cyclones in this season for this basin, but since we would like to do the homogeneous comparison and every model only run their runs every 3 days, so we actually didn't get that many cases for the comparison, and turn out the error in this basin is dominated by only 2 tropical cyclones, Florence and the Leslie. And unfortunately, shield doesn't do that well for these 2 hurricanes. For Florence, shield forecast the tropical cyclone moving too slow compared to other leading models. And for Leslie, it has a pretty complicated moving path, but the shield model doesn't make the right loop at the right time. So that's the major reason the accumulated track error from these 2 storms degraded the shield focus skill in this basin. And another thing for tropical cyclone forecast, we would like to take a look at the along track and the cross track errors. In the next 3 slides, I would like to show you the result from Atlantic Basin, East Pacific Basin, and the Western Pacific Basin, the 3 Northern Hemisphere basins. On the left-hand side upper corner, this one is the total error for the Atlantic basins for all the models listed here. And those other figures are for individual models, long track and cross track. The lower parts are their along track and the cross track biases. And we see for the pink line, the along track biases. Almost all the model start to show negative along track bias after day 3 to day 5. And the meaning of along track, the meaning of negative along track bias means the model moving too slow. And on the other hand, the positive means the model moving too fast compared to the observation. So for all the models in this basin, it shows a slow moving bias after day 3 to day 5. And on the other hand, for the cross-track arrows, the positive value means the storm has a right-hand side turning bias. And if we assume a storm moving from east to the west, right-hand side moving past along with their moving path means the storm moving to a higher latitude. In the North Hemisphere, that means it moved more to the north. So almost all the model in this basin shows north moving toward a higher latitude, north bias after day 3 to day 5 forecast. However, in the Eastern Pacific, the situation changed. We see the slow moving bias only show in the JMA model, but for other models, IFS, Shield, ICON, CMC, they all show a slightly faster moving bias before day 5. Only UN model show a relatively larger fast moving bias, as also the reason it caused the high track error for UN model in this basin. And for most tropical cyclones in the East Pacific, they usually do a straight moving from east to the west. They don't do that many recurvature like the storms in the Atlantic. So it makes sense their cross-track errors are relative small. And in the West Pacific, we can see the similar situation like in the Atlantic Basin. All the models show slow moving bias and move to higher latitude turning bias in this basin because of the strong move. Usually at the end of their lifetime, they move along to the north along with the coast in Asia and affected by the higher latitude trough or other large scale systems. Okay, next is about the tropical cyclone related precipitation. This figure are the accumulated total precipitation within the radius of 350 kilometers around the tropical cyclone center. And I compare all the model with the GPM observation data. And we know it is hard to see the differences if we just see those values on the map. However, we still can see that the UN model actually did a better agreement with the GPM for those large accumulated precipitation area than other models, especially in the West and East Pacific. So to quantitatively compare the location of precipitation between observation and models, we compute this equitable threat score, ETS. Higher value of ETS means the model show better agreement with the observation. In the left chart is for all the precipitation location, and the right one is only only comparing the area has accumulated precipitation more than 300 millimeter. So we can see the UN model does show higher score for more accumulated precipitation area than in other models in the two Pacific basins, East Pacific and the West Pacific. In the Atlantic Basin, the ICON model and our project got the highest score in both O and the only large accumulated precipitation area. And we also found that although CMC show a relative high track error in the East Pacific, but its ETS in this basin is the highest. And also JMA also captures some precipitation pattern well in the Western Pacific. And that things happen in both categories. Okay, so we also compare the tropical cyclone related precipitation based on the precipitation intensity. So here is the fraction of model or observed precipitation event in each precipitation intensity bin. So the black bar is the observation, and would like to see the color bars from the models as close as to the black bar. We see from the 1 to 20 millimeter per 6 hour intensity that most models show the over-predict precipitation events. Unfortunately, our shield model way over-predict the events in the intensity 1 to 5 millimeter per 6 hour bin. Although the shield model can capture some heavy precipitation events like the UN model does, but this over-predict situation is one thing we need to be further improvement in our models. Okay, about the tropical cyclone intensity forecast, I would like to quickly show you the results. Since we know the half-degree resolution data is not enough to demonstrate each model's tropical cyclone intensity scale, but I believe the differences among the models still can give us some idea. And we happy to see in the 10 meter maximum 10 meter wind category, our shield model outperformed other models, and in both total error and in the bias. And in the minimum syllable pressure forecast, shield also did show up lower total errors. And I would like to just for you a reference that the differences of the tropical cyclone intensity between half-degree data and the native resolution. I use the shield here as an example. The native resolution of shield is about 13 kilometers. So for the 10-meter maximum wind, the differences can be 3 meters per second for total arrow and 5 meters per second for bias. And for the minimum seeable pressure is 1 to 2 millibar for total arrow and 4 millibar for bias. Okay, the last things I would like to discuss is about tropical cyclone genesis forecast. And it is a relatively more complicated analysis than other metrics, so I might need to spend more time on it. So when we take a look at tropical cyclone track or intensity forecast, we only focus on those runs that happen initialized after the tropical cyclone genesis time. I use in this figure is like this black bar. But for tropical cyclone genesis forecast, those runs we should take a look at the 10-day forecasts, which are initialized earlier than the observed tropical cyclone genesis time, because we don't want the vortex information already exists in the initial conditions. Then we can know if the model can successfully generate a tropical cyclone by itself. So, so we take a look at all those 10-day forecasts initialized before the observed TC genesis time, but it covered the 10-day period is already the genesis time is included in this 10-day forecast period. And still we use the GFDL simple tracker to find those genesis, all those stones generated in the models. So if we see a genesis stone in the model show a match track to the observed TC, then it's a hit event. If the genesis model doesn't match to the observed TC, then it's a false alarm. And if a model run should generate a stone, but there's no stone generated in the model, that's a missing case. Hit event, false alarm, missing case are more traditional way for people to discuss tropical cyclone genesis scale. And so here, I would like to think what else we also can take a look at to better comparing the genesis scale between models. So in Chen et al. 2019 monthly weather review paper, I just proposed we can also take a look the lead time length. So we define the observed genesis lead time length is from the model's initial time to the observed TC genesis time. So the length of this genesis lead time can tell how early the model correctly predicts the tropical cyclone genesis. If the length is longer, that means the model earlier captured this genesis event in their run. Also, the model may not generate the stone at a perfect observed genesis time. It could be a little earlier and a little after. So the time spent from model's initial time to the model actually generated its forecast event, we call the model genesis lead time. And from the difference of these two kinds of lead time, we can know how precisely or how accurate our model can generate the event at the correct time. So the differences we call DMO here, the differences of model and observed genesis lead time. If the span of DMO is shorter, that means the model more accurate in generating stone at the observed genesis time. And if it's positive, that means the model forecast TC generated later than the observed time. If it's negative, that means the generated earlier than the observed genesis time. Okay, so I first like to show you a more traditional metrics, the hit event and the false alarm. So in this in this plot, the upper part is the heat ratio. The heat ratio is computed by the number of heat events divided by the number of total genesis event. That's the heat event plus false alarm. And the number of total genesis event I plot here for all the models for 4 different basins. And the heat ratio is here, and also the global average heat ratios. And before we compare the differences between models, we first find an interesting thing is in the East Pacific, it shows the highest heat ratio for all the model, but East Pacific also the fewest total genesis. So that telling us is the model can predict better TC genesis event in the East Pacific. They got a higher heat ratios in this basin rather than in other basins. On the other hand, for the Southern Hemisphere, lowest heat ratio for all the model, but a lot of total genesis. That means model got a lot of false alarm in these Southern Hemisphere predictions. And we're happy to see that the shield got the highest heat ratio in all basins, followed by the IFS and ICON model. And the CMC also doing a pretty good job in the East Pacific. And about the missing case, I have 2 plots to show you. The first one is the number of missed TC in the genesis forecast. That means the tropical cyclone exists, generated during the DIMOSIC period in observation, but the model completely missed by forecasted it. So for Atlantic, we have 16 storms, East Pacific 23, Western Pacific 34, and Southern Hemisphere 27 genesis event. But each model more or less can complete miss many of them actually. IFS actually has the fewest number of missed tropical cyclone in the Atlantic. And we find an interesting thing is the newer IFS model actually missed more tropical cyclone genesis in the East Pacific and the Atlantic. And we're happy to see SHIELD has the fewest number missed case globally. And CMC has the low missed tropical cyclone number in East Pacific, West Pacific, and the Southern Hemisphere. And we believe our SHIELD model do a better in earlier in heat ratio, and the missing cases might related to our storm intensity are stronger than in other models. And also can see by the missing case ratio. So here I compute the missing case ratio is the number of missing cases divided by the number of expected genesis observation. So from this timeline, if let's observe the genesis event here, and all the 10-day forecast before this time and including this time, supposedly can have a genesis this event. So that's the number of expected genesis observation. So for every storm is like a 4 or 3 for every model. But if any of them doesn't successfully generate this genesis event, then it's a missing case. So we can compute this ratio. And we find the SHIELD still show the lowest missing ratio in the 3 major basins, East Pacific, Western Pacific, and the Southern Hemisphere, but not the Atlantic. And we still find interesting the newer IFS configuration has higher missing ratio than the IFS 46R1 configuration globally. Okay, then it's about the genesis lead time result. As I said earlier, we use the observed genesis lead time to see how early a model can correctly predict the tropical cyclone genesis event. So here I use the 3 model in the North Atlantic Basin as an example. The observed genesis lead time for SHIELD is 110 hours, same same as in our project model, but they are it is 78 hours for UN model. So that means in this basin, shield and our project can predict the heat event 32 hours earlier than the UN model. And we see the shield show the earliest heat event also in East Pacific and the West Pacific, and our project shows the earliest heat event in the Southern Hemisphere. And shield IFS model show earlier heat event than the updated version in Atlantic, East Pacific, and the Southern Hemisphere, and it's about the same in the Western Pacific. That's also another thing we find, the newer IFS configuration doing slightly worse than IFS in the Genesis forecast. Okay, and my last result is about this Bmo analysis. So it can tell us how accurate a model in generating storms at the observed tropical cyclone genesis time. As I said earlier, if the DMO period time span is shorter, that means the model has more accurate ability to genesis the tropical cyclone at the right time. If it's positive, that's the model generated the tropical cyclone later than observed. Negative is the earlier than observed. And here I plot the friction of total heat events occurring within a certain DMO length. So 0 means exactly the model generated at the observed genesis time. And within 6, 12, 24, and 48 hours means before and after certain time period of the observed genesis, the genesis event, the model actually successfully hit the genesis. So we first take a look who does the most accurate tropical cyclone genesis time. Is the IFS, has the highest friction. But besides the two IFS model, the tropical cyclone genesis time in JMA and our project are also very accurate. Although JMA doesn't do that well in the tropical cyclone track and track forecast, but its genesis timing is quite accurate. And we also find that more than 98% of the heat event can happen in a 48-hour time span for any of the model. And also one thing very interesting to see is the heat event in most of model occurring before the observed tropical cyclone genesis time rather than after, except for JMA. JMA is the outlier for this part. Okay, that's my summary. We think DIMOSIC project provides us a great opportunity to engage with our partner in this community, especially for the model development community, to share our experience and hope in the future can fix our weakness based on those research results. And for the period we target from 2018 June to 2019 June, for the tropical cyclone track forecast, we see the IFS 46R1 and its newer version made the best global average tropical cyclone track forecast, followed by the ICON and shield model. And in the Atlantic, our shield doesn't do well compared to other leading models. That's because we doesn't do well forecast for the two major hurricanes, and is accumulated the track error degraded the track forecast skill. However, shield model does a very good job in the East Pacific and also doing pretty well in the Western Pacific and the Southern Hemisphere. And from the along track and the cross track error analysis, we see all the models show slow moving bias and moving bias to the higher latitude in both Atlantic and the Western Pacific. basins. And in the East Pacific basins, except for the JMA, most models showing fast-moving bias, especially the UN model, which also the reason the UN model has a higher track error in the East Pacific. And about the intensity forecast, we know that a half-degree resolution doesn't demonstrate each model's real tropical cyclone intensity scale, but the difference is still telling us that the shield has the best tropical cyclone intensity forecast, especially in the maximum 10-meter wind speed. And about the tropical cyclone related precipitation, we find the UN model has better captured the regions of accumulated precipitation more than 300 millimeters than other models. And our shield model can also capture some heavy precipitation event, but it largely overpredict the precipitation event at 1 to 5 millimeters per 6 hour intensity. That's the things that we need to improve in the future. And for Genesis forecast, we're happy to see our shield model shows the highest heat ratio in all the basins and the lowest mixing ratios and the earliest heat event in the 3 major basins. And we believe it is because we can better predict the tropical cyclone intensity. And based on the heat ratio, all the models predict better tropical cyclone genesis in the East Pacific, but models got a lot of false alarm in the Southern Hemisphere, which is quite interesting. And generally, IFS can show slightly better tropical cyclone genesis forecast than its updated version, 46R3, and which is an interesting thing, and we should provide information back to ECNWF. And although the JMA and CMC and our project, they didn't show that well in track forecast, but they actually can do a pretty good genesis timing than other model. Except for the IFS still do the best genesis timing for the tropical cyclone genesis forecast. So that's all I have. Thanks a lot.
Thank you, Jan-Huey. I really want to thank you for sharing your fascinating research with us. I appreciated learning more about the models. I want everybody to look at your screens right now, and that QR code on your screen that has just come up will direct you to adding your questions to our Slido for today's speaker. And while you're doing that, I do also want to invite you to attend our next seminar series. Our next one will be Wednesday, the 20th, and that will be Dr. Malasala Rao. Dr. Rao is a CPAESS project scientist at NOAA's National Center for Environmental Predictions, the Environmental Modeling Center. And he's going to speak on the predictability of extreme rainfall events over India during the summer monsoon season by using NCEP GEFS version 12 model in the present global warming era. So with that invitation, please add your questions, and I'm going to hand it over to Dawn to field the questions.
Thanks for the great talk. It looks like our first question is, what improvements would you like to address in the shield model next?
Yeah, so definitely the precipitation is the one thing we would like to take a more close look at. And we believe that's related to it relates to the microphysics scheme we're using, and it shows a pretty good global average scale. But for tropical cyclones, when it comes with more strong convections, maybe that's the thing we can further adjust it.
Excellent. Thank you so much. Our next question is, What is the reason for the model to have a higher hit rate over the Eastern Pacific? Is it related to availability of observations to initialize the models?
That's a really, really interesting question. And I actually really don't know. And it's not just happening in one model, it's every model has the same behavior, ability of observation to initialize the models. But I believe the observation in other northern hemisphere basins may get even more attention because all the tropical cyclones can affect human being active area more. So I think that's the thing we can further think about it.
Okay, excellent. Our next question is, what is the reason why SHIELD can predict TC genesis with a longer lead time than other models?
Okay, this one we pretty sure is about intensity. So when the storm start to generate in the model, is usually the weakest time in its entire life cycle. And if a model better capture its intensity, then it's be detected by the tracker earlier. So I believe that's the reason the SHIELD show longer lead time than other models for tropical cyclone genesis.
Okay, excellent. You're getting lots of questions, which is wonderful. Why did you choose the area within 350 kilometers of TC center over another distance from center when looking at rainfall?
So I would like to see those precipitation from the tropical cyclones circulation. And I believe 350 kilometers is like a regular size for people to define a radius of tropical cyclone. And I also did a little bit sensitivity test, use 300 to 400 kilometers, and don't see that much differences. And I decided just to settle with 350 kilometers.
Okie dokie. The next question that we have is, what do you think is the impact of model resolution compared to model formulation?
The model resolution the impact of model resolution compared to model. Oh, that's a good question. I think it's dependent on what kind of things you would like to take a look. For tropical cyclone forecast, if you take a look about track forecast, I will say because it's relied on large scale circulation on large, so the model resolution may not be that critical as it affects tropical cyclone intensity. But for model formulation, that's really complicated because it's almost impossible to do a clean comparison for two general circulation models. So in these 7 models in all the DIMOSIC project, the 2 models might be able to do some comparisons only the IFS and the ICON model. That's because they almost use the same physics package. Rather than that, every model as formulation, either in dynamic or physics, are quite different. And there's a table list in the next paper. So I don't know if a model resolution impact can compare to the model formulation, but I definitely say it's really hard to tell what the differences from our result is caused by which model formulation. And that's also very challenging questions, and the next paper try to answer.
Wonderful. We have one last question. So if folks have more, please enter them in. Are most of the models atmosphere only or coupled models? I'm wondering what are the impacts of air-sea coupling on TC predictions, including tracks, intensity, and genesis?
Not all the models are atmosphere-only models. I believe IFS, ICON, and us, and I only know these three. They are atmosphere-only models. I'm not sure about UKMO and the impact of air-sea coupling definitely can have impact, especially on intensity and genesis. I don't think it will cause too much impact on track. That's what I believe. I think that's a good suggestion for me to take more detail about the differences on this part and see if they got some impact of it. Thank you.
Thank you. I think that is all the questions that we have right now. So I'm just going to turn it back over to Cindy. Thank you.
Thank you very much, Dawn. Jan-Huey, thank you very much for a very fascinating talk. I've learned a lot and I'm looking forward to your paper and looking forward to chatting more with you about your research. On that note, I would like to thank everybody for attending our seminar series today. And I want to remind you to go to our website for future talks at CPAESS at UCAR.edu. And you're going to be able to find a link to this talk that we will upload on YouTube later. I also want to take the opportunity to thank Brett from the UCAR Multimedia Service for his assistance today. It is very well appreciated. And I want to thank Alex and Dawn for making this all happen and taking care of all the questions for us. So good afternoon, everybody. And I think Jan-Huey would also not mind if you send her questions if you still have questions.